In the previous module, we have introduced a new kind of a strategy which is very specific to the extensive form games called the behavioral strategy. So in this module, we are going to discuss what are the other properties of this strategy and why they are desirable. Well, the first desirable property is that this is more natural. A player can independently randomize over different actions in every information set rather than randomizing over everything in one go. So if the imperfect information extensive form game is really large, then possibly listing down all the possible strategies in that game is really not feasible. Rather, it is much more feasible for any reasonable player is to plan at every stage of the game, and that is the information set. Now, this is one reason why behavioral strategies are. So the number of variables that the player needs to deal with, if you consider a player. So let's look at this small example where we have 4 information sets for a player, and there are 2 actions in each set. So therefore, you can have 2 to the power 4 number of possible strategies. And because these are all probability distributions, so if you fix n-1 variables already, you have the last variable fixed already. So therefore, the degrees of freedom will be 2 to the power 4 minus 1. This many number of variables will represent the mixed strategy of that player, which is exponential in number of the information sets. But for the behavioral strategy, you just need to consider 4 variables, because at every stage you just have to consider 1 variable, which is denoting the probability of picking one of the actions. The other action will be 1 minus that. So the number, even in terms of the numbers of variables that the player has to decide upon, is much smaller in behavioral strategies. So the agents who are computationally limited will always tend to behave according to these behavioral strategies. And also, these behavioral strategies need not be fixed at the very beginning. It can be fixed at every the actions can be taken at every information set. Whenever the agent is playing at that information set, it can choose the action with respect to that behavioral strategy. Now, the most natural question is, can we construct one from the other, or does the equivalence always exist? The previous example we discussed in the last module, we have shown an equivalence between these behavioral strategies and mixed strategies. Can we always find such kind of a thing? And in this and the following module, we will actually show that yes, there are really a very large class of reasonable games where this equivalence is obvious. So if you are playing one of those kind of games, and those kind of games are actually pretty large, then whether you talk about mixed strategies or whether you talk about behavioral strategies, it does not matter, because there will always exist an equivalent for one kind of the strategies and the other. So that is the final goal that we are aiming at. But in this module, let us look at some kind of games where this equivalence does not hold. So for instance, take a look at this game. So let me just go over it. So for player 1, you have 1 and 2 information sets. So this is another information set for player 1. And note that player 1 is the player in both these information sets. So this is singleton, but it has 2 elements. And player 1 is either playing L1 and R1 here, and in the same information set, the player has to play the action set has to be same. So therefore, L2 and R2 is the action there. So what is the set of mixed strategies here? So of course, it is going to randomize over this L1, L2, L1, R2, R1, L2, and R1, R2. Okay? So these are the 4 possible pure strategies. The mixed strategy will be a probability distribution over those pure strategies. Now, if you look at the behavioral strategy, and here I'm just ignoring this inside this notation. I am just dropping that the information set, because that is clear from the context. In particular, this will be B1 if you want I11 of L1, but I am just dropping this information set because I already know this L1 and R1 are actually the actions available at this information set. So therefore, it is equivalently represented by B1 of L1. And the other behavioral strategy at this information set is going to be B1 L2. Of course, the B1 R2 will be just 1 minus that. Now, you can see that here the mixed strategy has a much better control over this game. So it can independently put probability masses on all these profiles, all these action profiles. In particular, if you look at this example where this L1 R2 and R1 L2 is 0. So maybe it is putting the probability masses to these two cases to be equal to 0, and maybe for both these cases the probability masses are positive. So maybe half and half in these two cases. Then if you apply the previous principle, can you actually find a behavioral strategy which will give an equivalent representation? So therefore, so you can reach this leaf node and this leaf node according to this mixed strategy with probability 0. But this probability 0 can never happen in a behavioral strategy. What you can do is you can put some mass here and some mass here. If this probability is equal to half and this is also equal to half, you'll have to carefully choose this probabilities L1. So L1 and L2 both has to be positive, and both of them cannot be equal to 1, right? And the moment you pick those values L1 and L2, no matter whichever way you choose, you are also ensuring that this probabilities and the probability of this is also non-zero. Then the probability of L1 R2, this probability becomes something positive. You cannot ensure this to be equal to 0, because in order to make this to be equal to 0, you need this R2 or L1 to be equal to 0, right? So no matter whichever way, so one possibility is you want to make sure that this is 0, then you put probability mass of R2 to be equal to 0. In that case, this becomes equal to 1. Then L1 has to be equal to half, and then you have R1 to be equal to half. But notice that you have already fixed R2, the probability here, because that is coming from the same behavioral strategy, that has already been set to 0, and L2 is 1. So the moment you set this to be equal to half and L2 is equal to 1, so therefore this becomes a positive thing, and you cannot set it to 0. So very clearly that you won't be able to find any behavioral strategy which is equivalent to this mixed strategy for player 1. So this is one example. So this is an example where you have a mixed strategy which has no equivalent behavioral strategies. Now let us look at the second example. This is also just with one player. So imagine the player 1 is first playing L or R, and this is the first node, and this is in the same information set when he is playing L. So the story that goes along with this kind of a game is that player 1 is kind of a forgetful. I mean, an example where player 1 is not able to recall what has happened. In the first example, it is forgetting whether it has at all played or not. In the second example, it is forgetting which action it has played. Okay. Now again, you can think of something like a behavioral strategy where you are putting some probability mass on both L and R. So some positive probability for both L and R. Then you can find that because at every node, so there is a certain positive probability of playing L, and therefore you can actually see this sequence of actions being taken with some positive probability. But this cannot happen in any mixed strategies. Why? Because if you look at so what are the possible pure strategies here? Notice that this node here and this node are both in the same information set for player 1. Therefore, there is only one action that is available for player 1, which is L or R. One set of actions available. So the mixed strategy should either randomize over this L or R, and the moment it plays L, so this is like picking a pure strategy. The moment it plays L, it also has to play the same strategy in the second stage, because that is the action that has been chosen. So this is the limitation of the mixed strategy in this context, in the context of this kind of a forgetful player, that the moment you pick L, you can only have L and L played in both these rounds of this game to be the only outcome. So no pure strategy, and we'll explain this in detail later, that no pure strategy will have L played in the first round and R played in the second round. So therefore, every mixed strategy profile will put 0 probability here, while behavioral strategy can put, because that is played independently at every node, is going to put some positive probability here, right? So just to remember that this example 1, the player remembers that it has made a move but forgets what move it has made. In the example 2, player 2 forgets whether it has made a move or not. Right? Actually, what I said before, I think, was just the opposite. So just correct that. So it essentially, so player 1 is in the example 1 is actually remembering that it has made a move, but it has forgotten which move. Therefore, it is indifferent between L1 and R1. While in example 2, it has actually forgotten whether it has actually moved or not. That is why these two nodes are being connected with this dotted line. So if it had remembered that it has actually moved, then these two nodes should not have been in the same information set. Now we have just seen 2 examples where this equivalence of mixed strategy and behavioral strategy does not hold, and that does not hold because players are forgetful in this case, different kinds of forgetfulness. Now the more natural question is, when does behavioral strategy has no equivalent mixed strategy? So, and let us look at the second example in more detail, and from that we will be able to find out what are the requirements for behavioral strategies having an equivalent mixed strategy. So consider a node, a non-root node, which is X, and we are going to define, use this terminology, action at X1 leading to X. So this is an unique edge that is emanating from this node X1. So X1 is some intermediate node which is lying in the path from the root to X. So because this is a tree, it's a game tree, there is only a unique path. Therefore, there will be an unique edge that is emanating from X1 that is on the path from the root to X. Right, so that is edge will denote what is the action that has been that can lead you from X1 to X. X1 and X need not be parent or child. They might not be directly connected, but they will be living in some subtree. Therefore, only the direction matters. It does not need to be a parent and a child. Now, if you look at this example 2. So there exists a node which has a path from root to itself that crosses the same information set twice. Let's go back here. So we have a path, this is the path, and this is crossing. So first time it is crossing at this node, and next time it is crossing here. So this path is crossing this the same information set twice, starting from the root. Now consider the following. If the path from the root to x passes through vertices x1 and x1 hat, so these are two different nodes that are in the same information set of player I, and also the action leading to x at x1 and x hat. So in the first case, the action that this player was taking to in this path, which was leading to x. So let's say this node is x, and this first node is x1, and this node here is x1 hat. So at x1, player 1 is taking the action L, while at x1 hat it is taking a different action, that is R. If that is different, then it is quite evident, using the argument that we have just used, that there cannot exist any pure strategy that can lead to x. Right? So you cannot reach x via a pure strategy. So you can look at the example again. Your pure strategies are either L or R. The moment you fix L, it is going to do this L in both these rounds, in both this x1 and x1 hat, and then you reach this node. If you choose R, you come to this node. In no pure strategy you can ever come to this node, which is x. So therefore, since the pure strategy can never lead you to x, and mixed strategy is just a randomization over these pure strategies, then every mixed strategy will put zero mass on that node, that x. So that is the reason we were getting always zero mass on this outcome of L, R. But in behavioral strategy, it is randomized over every vertex of so it is randomized over different information sets independently, and also at different vertices of the same information set independently. And therefore there is a positive probability, there could be a positive probability that x can be reached. So in behavioral strategies you can reach x with some positive probability, but this example actually shows that it is required that if you have this kind of a setup where the path from the root to a specific node is crossing the same information set twice, and the action taken at those nodes at the same information set are different, then you may have a behavioral strategy which does not have an equivalent mixed strategy representation. Right? So this observation can be stated formally as a lemma. This lemma says that if you have a path from the root to some vertex x that passes through the same information set at least twice, and if the action leading to x is not the same at each of these vertices, then the player of the information set has a behavioral strategy that has no equivalent mixed strategy. That is exactly rephrasing the arguments that we have provided in the previous section. Now this lemma will be useful in helping us providing the characterization result of equivalence. When does this equivalence hold? So this is the theorem, the statement of the theorem. This says that if you pick some imperfect information extensive form game, says that every vertex has at least two actions, and every behavioral strategy has an equivalent mixed strategy in that imperfect information extensive form game, if and only if. So this is the shorthand that we use for if and only if. If and only if each information set of that player intersects every path emanating from that root at most once. So the same problem would have been solved if you had exactly one intersection point. So in that example, it is intersecting the same information set twice, and if it intersects exactly once, then you are always guaranteed to find an equivalent mixed strategy representation for any behavioral strategy. So the proof is actually long, and it actually builds on top of the things that we have already discussed. So I am not going to prove that formally again. Rather, I'll put it as a reading exercise from the book. So this is Theorem 6.11 from this Maslow's book.